This is Unit 7, Chemical Reactions for Chemistry. So Part 1 is all about just chemical reaction basics, some things you need to know in order for you to do chemical reactions, things you're going to see when you're doing chemical reactions as far as the equations, all that fun stuff. So the basic definition of a chemical reaction is the changing of substances by breaking of bonds in the reactants and the formation of bonds in the products. Now, reactants and products are vocabulary words that we'll use in this unit, and we'll talk about those in just a little bit. But really, a chemical reaction, if you remember, is a lot like a chemical change. Okay, so let's review what a chemical change is. So evidence of a chemical reaction or chemical change would include, first, the release of a gas. Okay, we actually did this experiment in class, and I walked it around the room where zinc was added to hydrochloric acid at the beginning of the year when we talked about matter and we talked about chemical changes and physical changes. Hydrogen gas gets released, and then you have a solid zinc chloride, which is a salt, but it also gives off heat. But it's mainly that release of a gas. It bubbles. Hydrogen peroxide does this too when you put it on source. So that's an evidence of a chemical change or a chemical reaction. The other thing would be a color change. So we might put two liquids together. These liquids are yellow and colorless, but when they're mixed, they actually create like a red color. Okay, that is indication that there's a chemical change going on or chemical reaction. Then also you could put like a solid into a liquid and you would end up with a different colored liquid. This is actually copper in a chloride solution like hydrochloric acid, and it'll make copper chloride. Okay. Then also it could be the formation of a precipitate. Now, precipitate is something we've already talked about before, but it's a vocabulary word that you need for this unit again, and it is a solid that's produced from the reaction of two aqueous solutions. So it's a solid that's made when you put two liquids together, really is a thought process. Aqueous is another vocabulary word that we'll get to as we do our notes. So the abbreviation of a precipitate is a PPT. All right, so if you see that later on when we do reactions, you'll understand that that's a solid and it's just a precipitate that's formed. And so here we have an aqueous sodium iodide solution and an aqueous lead. I think it's lead chloride. I hate to move this because once I move it, it starts being weird. So, but when you put the two solutions together, then it creates this solid lead to iodide, which is this yellow color. And I believe it's sodium chloride, so it ends up being just a salt solution as well. Now, changes in light and heat are also evidence that a chemical reaction has occurred, okay? So all reactions are either going to absorb or release energy in some way, actually. And so when you put sodium peroxide, which is a yellow powder, and zinc powder, which is gray, in a bowl together, they will naturally just ignite. But it takes some time. But if you'll go ahead and put water in it, water acts as a catalyst, which will speed up the reaction, and it will cause this to happen. So if you just kind of watch the video, it kind of goes through. So we have the yellow and gray solution originally. We add the water stream here, and then it ignites. Okay, so changes in heat and light. So those are those four main things that we talk about. So when you write a chemical reaction or a chemical equation, you'll always start with the reactants. This is a vocabulary word that you'll need, like I said, and the reactants are the things you start with. They react together to create the chemical change or the chemical reaction. And then you end up with the products. Products are what you take home from the grocery store. So they're what's formed, it's what's made, okay? And so they're your finished materials. So that's your products. Now, the arrow in the middle means yields, okay? So the reactants will yield the products is a way to kind of think about it. So an example here is Na plus Cl2 yields NaCl. The single sodium and the diatomic chlorine will be our reactants, and then our sodium chloride, which is an ionic compound, is going to be our product. Okay, so that's just an example of if I said, you know, what is this, you would be able to say what the reactants and products were. So possible symbols that you're going to see in chemical equations would be plus, the plus sign, and the arrow sign. The plus sign just means is added to or they're mixed together, and the arrow means yields, and these are used in every reaction. And then you could have the S in parentheses, the L in parentheses, the G in parentheses, and the AQ in parentheses. And this would mean that they could be a solid, a liquid, or a gas, or even an aqueous solution. Now, aqueous is one of those vocabulary words, and aqueous just means it's dissolved in water. Okay? And this is listed after the compound to tell you what form or phase of matter that it's in. Then you could also have the double-sided arrow, the NR, the triangle, and some sort of catalyst. This is typically going to be some sort of compound, but we kind of list them as catalyst. Now the double arrow sign means reversible, the NR means no reaction, the triangle means heat or light, and the catalyst speeds up a reaction. The water in our previous example was a catalyst, just to let you know. Now the triangle and the catalyst are typically written above the yield sign, so they're written above the arrow. Okay? And that's because they're not a part of the actual reaction. So let's look at this, and let's talk about, so I have diatomic hydrogen. Remember, we had the diatomic elements, which were our H Broncliffs, and our H Broncliffs were hydrogen, bromine, chlorine, oxygen, nitrogen, iodine, and fluorine. Okay, but anytime those elements are by themselves, they have to be in a diatomic state, which means there's two atoms of them. So we have our hydrogen and our oxygen, which is then going to create products of H2O. Okay, so what's the arrow pointing to? Hopefully you're saying the G, which stands for that this is in a gas form. So the hydrogen is in a gas form. This is pointing to all of the elements that are on the left side of the arrow, which would be our reactants. This is pointing to our arrow that is in between what we start with and what we finish with, and it stands for yields. Okay, here's another example. I have a compound, then I have my arrow sign with a compound over it, then I create another compound and another element. Okay, so that is pointing to the compound over the arrow, which is manganese 4 oxide, actually, and that would be a catalyst because it's going to be used to speed up this reaction, but it's not actually going to be used in the reaction, and that's why we put it over the arrow itself. Then we have this circle around everything after the arrow or to the right of the arrow, which would make it all of these things the products. All right, and one last one. I have a compound. This is an ionic compound because it's got calcium, which is a positive ion. It's a positive 2 ion from your periodic table, and it has CO3, which is a polyatomic ion. And anytime you have a polyatomic ion in a compound, that makes it ionic. You're going to need to remember this stuff from our previous unit about writing chemical formulas and naming. We then have the arrow with a triangle over it, and then we have a calcium and oxygen put together, which is a calcium oxide, and that is an ionic compound as well. And we have a CO2, which is a covalent compound or a molecular compound, and it is carbon dioxide. So you do need to remember how we name things and things like that also. So this is a good way to review that information. But what I'm pointing out right now, this is actually the triangle that's over the arrow, which means that we added heat or light to this reaction to make it happen, but it wasn't actually included in the overall reaction. Then this arrow is pointing at the S, which is after the calcium oxide, which is telling me that the calcium oxide is in a solid form. All right, that was part 1 of your chemical reaction notes. So hopefully you got that filled in, and you should be able to answer your classwork now, which has some definitions. So classwork 1 has 5 definitions, and you should be able to answer most of them. But I'm going to go ahead and continue into part 2 on this recording because they kind of go together. So I'm going to keep going. Now part 2 is about writing and balancing chemical reactions. So the main thing to understand is all chemical equations must obey the law of conservation of mass. Now we talked about the law of conservation of mass back when we did our matter unit. And the law of conservation of mass states that matter cannot be created or destroyed. So we can't just magically create atoms or elements, but we can rearrange them to create new ones. And so that's the important thing. And we also can't just destroy them and make them disappear. But we can, like I said, rearrange them and put them in a different format. Because of that, when you write a chemical equation, all the reactants, everything that you have element-wise as a reactant, has to exist in element form some way in the products. Now, it might look different, it might be combined different, but there has to be the same number of that element on both sides to satisfy the law of conservation of mass. So when we get done with this unit, we should be able to do things like this, what I'm about to show you, okay? And so we should be able to write an equation for the formation of sodium hydroxide and hydrogen from the reaction of sodium with water. Okay, so this takes us back to remembering how we have to write equations and how we have to write formulas, whether it's ionic or covalent, you know, those kind of things. So sodium hydroxide is ionic, and so we need to look up sodium. So we're going to write all the formulas for all the reactants to the left of the arrow, and then we're going to write all the products to the right of the arrow. For this particular one, our products are sodium hydroxide and hydrogen, and our reactants are sodium and water. Okay, because we said the formation of these two, and that and sign really means our plus sign also. And then we said from the reaction of, so these are our reactants, is sodium and water. Okay, next thing we need to do is we need to translate the equation and be sure that the formulas are correct. So we need to write all the formulas for all of these compounds or reactants and products that we have. So sodium is Na, water is H2O, sodium hydroxide, sodium is Na with a positive 1 charge, and hydroxide is OH with a negative 1 charge. So we would then crisscross those because we would have Na positive and OH negative, which is on the back of your periodic table. And then we crisscross the charges down, which means there's just 1 and 1 as the subscripts down here. So remember, subscripts are down here. Now water is H2O, so that's why it has a subscript of a 2 here. And then hydrogen is one of those diatomics, remember, that I told you about? And those, I say, are the H Broncliffs. I think that Mr. Lawson says something like Brinkelhoff or something like that. I mean, he just uses a different acronym, but there's different ways to remember it, but I've always just used it as the H Broncliffs. So, but any of these elements that you see by themselves in these equations have to have 2 as a subscript because they are diatomic, so that's important. So once we get this written, though, we are going to, and once we make sure that all our subscripts are right, then we have to do something else, okay? So once we have the formulas and they're correctly written, we are not going to change the formulas at all. We won't ever change those subscripts. Notice it says it in all caps, it's bolded, and it's underlined. Do not change the subscripts. Remember, the subscripts are the little numbers on the bottom in a formula. and they typically come from the charges or the prefixes. Okay, so we are going to now use what's called coefficients, which are going to be large numbers that are in front of the compounds or formulas or elements, and they are always going to have to be whole numbers to balance the equation out. Remember, in order to follow the law of conservation of mass, we have to have the same number of elements on both sides. So if I have Na plus H2O yields NaOH plus H2, I have to then look at what elements do I have on what side. Okay, so I have one Na over here and I have one Na over here. So that's good. I'm good to go with that. I have two H's over here and I have two and one more over here. Okay, well that's a kind of odd number, so let's try to make that more even. So if I needed to make that an even number, the best way for me to do that would be to put a 2 right here in front of the NaOH. Okay, if I put a 2 there, that now makes me, I have to, anytime I put a coefficient, I have to go back and recount. Okay, so if I do this, I now have 2 NAs. Okay, so if I have 2 NAs, I'm going to have to put 2 over here. Okay, if I do that, I also have 2 O's because I have to distribute this 2 to the whole compound. So I'm going to put a 2 over here because this will now go to this 2 for this oxygen. It has a subscript of a 1, so 2 times 1 is 2. Then I have 2 times 2 for my hydrogens here on the reactant side, which is 4. Here I have 2 times 1, which is 2, plus an additional 2 over here. So now I'm balanced because there's 4 hydrogens on both sides. So when we look at it, we have 2 NAs on both sides. We have 4 H's on the reactants and 2 on the 2 oxygens. Then we have 2 on the products, 4 on the products for the hydrogen, and 2 for the oxygen. I do actually recommend that you do a list of these elements, and I'll kind of show you that as we walk through. So when you're finished, you should have equal numbers of each element on each side of the equation. That's satisfying the law of conservation of mass. So to determine the number of atoms of a given element in one term of the equation, you multiply the coefficient by the subscript of the element. So in our previous equation, how many hydrogen atoms are there? We take these 2 and we multiply it by, we take the 2 coefficient and multiply it by the subscript of 2 on the hydrogen. 2 times 2 is 4. Okay. When we come over here, we say 2 times the 1 of the subscript here in the NaOH formula. So that's 2, because 2 times 1 is 2. And then we have another 2 over here as a subscript. So that would be 2 plus 2, which also equals 4. So helpful hints about balancing. 1, make a list of elements on each side of the equation. 2, balance the elements one at a time. 3, balance polyatomic ions that appear on both sides of the equation as a single unit. Now I will tell you, water can sometimes be written instead as HOH. If you write water as HOH, then you're going to see it as a polyatomic ion of hydroxide. So that'll sometimes help you when you're doing certain equations. So you can write water as HOH so that you'll see hydroxide on both sides. That might have been helpful in our last example as well, so that we could have seen things a little bit differently. And then, so for example, on this one, I could look at the NH4s, and NH4 appears over here as well. So I could just keep the NH4 together because I would say that there are 2 of them on this side and there's only 1 of them on this side. So that would help me start to balance that. Also, I could do the same thing with my sulfates, and SO4 appears there and it appears there, and there's 1 on each side. So that might be easier for me to count it that way instead of counting it as sulfurs and oxygens and hydrogens and separating it all out. Okay. And finally, I will say to balance the hydrogens and the oxygens last. Okay, they are typically your most troublesome ones, so you should always go ahead and balance those last. Also, use a pencil. You're going to erase, you're going to make mistakes, you're going to have to change numbers, so use a pencil while you balance equations. All right, so let's do some practice. We're going to balance the equation for the formation of magnesium nitride from its elements. Now, magnesium nitride is an ionic compound, so in order to write its formula, we first have to look up the elements and their charges. So magnesium is an Mg with a 2 positive off your periodic table because it's in column 2. And nitrogen is N, and it's a 3 minus because it's in row 5A. Okay, so then we're going to crisscross these charges down. The positive and negative will disappear, and those superscripts will now become the subscripts on the opposite element. So we will create magnesium 3, well, Mg3N2. All right, now that's a product, so we're going to put it on the left. And it said it was formed from its elements. So the elements that would create it would be magnesium and nitrogen. Nitrogen is one of those diatomic elements, so when it's by itself, it has to have a 2. Once we get this written, never change the subscripts. Okay? But now we want to do magnesium on this side. And nitrogen. And we want to do magnesium and nitrogen for this side. So on this side, we have 1 magnesium and 2 nitrogens. On this side, we have 3 magnesiums and 2 nitrogens. Okay, so our issue is our magnesiums right now, so we will need to put a 3 in front of our magnesium. When we do that, 3 times 1 is 3, and now we have 3 magnesiums on both sides, and we have 2 nitrogens on both sides. So we're balanced. So balance the reaction of sodium metal with chlorine gas to form sodium chloride. Okay, so sodium metal is Na. Chlorine gas, chlorine is Cl, but it's a diatomic, so it has to be Cl2. Sodium itself is Na with a positive 1 charge for our ionic compound. And chlorine is Cl with a negative 1 charge, so when you crisscross it becomes NaCl. So we have Na positive, Cl minus, which would create NaCl as our product, and the reactants would be Na plus Cl2. We then have Na and Cl on this side, and we have Na and Cl on this side, which we have 1 and 2, and we have 1 and 1. So our chlorines are the first thing that's not matching, so we're going to put a 2 here. When we put that 2 there, we then have to recount. So that makes it to where we are going to now have 2 times 1 is 2, 2 times 1 is 2. So that fixes my chlorines but messes up my sodiums. So I then need to come to the other side and put a 2 there, which then 2 times 1 makes 2, and now I am balanced. All right, so we have H2 plus O2 yields H2O. By the way, this doesn't happen spontaneously. Okay, so sometimes if you look at it the opposite way, we have to have electricity to do that, which would be a catalyst, but just FYI on that. So I have H and I have O, and I have H and I have O, and I have 2 and I have 2 and I have 2 and I have 1. So my hydrogens are fixed, but my oxygens aren't. So that means I need to put a, oops, let me go back, sorry. Forgot that I didn't have these. So I need to put a 2 here. When I do that, I got to recount. 2 times 2 is 4. 2 times 1 is 2. That fixed my oxygens but messed up my hydrogens. So I now need a 2 over here. 2 times 2 is 4. And now I am balanced. Okay. My next one is C2H4O2. So I have making carbon dioxide and water. which would give me CHNO and CHNO. So I'd have 2, I'd have 4, and I'd have 2. Over here I'd have 2, I'd have 2, and oops, that's the wrong count. I only have 1 carbon, sorry. 1 carbon, 2 hydrogens, and 3 oxygens. Okay, well, we automatically can see that our carbons are messed up. And I will tell you, when you do these, you're always going to do them carbon, hydrogen, oxygen order. So fix the carbons first. So when I do that, I put a 2 here. And then you have to recount. So 2 times 1 is 2. 2 times 2 is 4, plus another oxygen on the other side makes this 5. Okay? Then I have to fix my hydrogens, so I need to put a 2 right here. So when I do that, I get 2 times 2 is 4, and I get 2 times 1 is 2 oxygens there, plus another 4 oxygens, which is, so this has 4 oxygens plus 2 oxygens, so that makes 6 oxygens overall. And then I can come over to my, because that fixes my hydrogens and my carbons, but now my oxygens are messed up. So I can put a 3 right there. That will be 3 times 2, which will give me 6, and now I will be balanced. Okay. All right. My next one, I have NH3 plus O2 yields NO2 plus H2O. So I have N, H, and O, which is N1H3O2. Then I have N and H and O. And I have 1 N, I have 2 H's, and I have 3 O's. Okay, so my first thing to think about is the fact that I don't have an easy number between 3 and 2 for my hydrogen, so I have to come up with a multiple. And the multiple that they share would be 6. So what can I multiply by 3 to get 6? And that would be a 2. So when I do that, I have to recount. So now I have 2 nitrogens and 6 hydrogens. All right, so here on the other side, I'm fixing my hydrogens, so I'm going to do 3 here. So that will make 6 hydrogens, and then I need to fix my nitrogens, so that'll make 2. Oh, sorry, I need to fix my oxygens too, because that would have been 2 and 3, so that would have been giving me 5 oxygens. Now I need to put a 2 there to fix my nitrogens, so that would have been 2, and then that'll be 4 plus 3 for my oxygens, which will be 7. Is there anything I can multiply by 2 to get 7? Well, hopefully you realize, yeah, Miss C, you can do 3.5. Well, hold on. Here's the problem. You can't have decimal numbers or fractions in your as a coefficient. You have to have whole numbers, remember? So when this happens, what you need to do is you need to go through and you need to actually multiply every single one of these numbers by 2. So if that's the case, I'm going to multiply the entire compound times 2 on my coefficients. And I probably shouldn't make that look like a square. Sorry. It's going to be multiplied by 2 on my coefficients. So now my coefficients are going to change to 2 times 2 is 4. 3.5 times 2 is 7. 2 times 2 is 4. And 2 times 2 is, or 2 times 3 is 6. Okay, so when I do that, now let's recount everything. Okay, just to double check. So on my actual nitrogens, I have 4. On my hydrogens, I have 4 times 3 is 12. And on my oxygens, I have 7 times 2, which is 14. On this other side, I have 4 times 1 is 4. I have 6 times 2 is 12. And on my oxygens, I have 4 times 2, which is 8, plus 6 times 1, which is 6, which equals 14. I am balanced. It is complete. and I'm good to go. Okay, that one is a more difficult one, I will tell you. So it takes a little bit of time to get used to doing ones like that. All right. All right, now I have K and F2, and some of y'all will get to where you don't want to do the list of elements because you're like, okay, I can just see that, Miss C. And if you can, that's great too. There's one, there's two. You don't have to do this. It's just a recommendation. Okay, so automatically we can see our F's are not balanced. So we need to, 2 times 1 is 2. But then when we recount, that messes up my K's. So then I need a 2 there, which makes me balanced. Remember, anytime you put a coefficient, you have to recount. Okay, so here, this is one of them, like I said, that I might rewrite as HOH for my hydroxides. Because then I could write CaH and OH. Okay, then I could do CaH and OH. Okay, so if I do that, on this side I have 1 calcium, I have 1 hydrogen, and I have 1 hydroxide, because that hydroxide is not in parentheses. Over here, I have 1 calcium, I have 2 hydrogens, and I have 2 hydroxides because that hydroxide is in parentheses. So that makes it really easy for me to see that my hydrogens and my hydroxides are messed up. So I could put a 2 right here in front of this, and when I do that, that now makes it to where I have 2 hydrogens and 2 hydroxides, and I'm balanced. Okay, so it's just a little bit easier than trying to count your hydrogens and oxygens and things like that to kind of make it look like HOH instead. Just a suggestion. This one, also, again, I have a lot of polyatomics, but NH4 is not NH4 on the other side. Okay, also, I could go ahead and rewrite my water as HOH, but that would really make it to where, since hydrogen is involved in multiple places, it makes it to where it's a little bit more difficult to do that. So I'm not sure I would recommend breaking it up on this one. So I would do my individual elements of N, H, Cl, Ca, and O. It's a lot of elements. N, H, Cl, Ca, and O. So over here I have 1 nitrogen. I have 4 plus 2 because I have to distribute the 2 on the OH right here to both oxygen and hydrogen. So that will be 6 hydrogens. Chlorine, I have 1. Calcium, I have 1. And oxygen, I have 2. Over here, I have nitrogen as 1. I have 3 hydrogens plus another 2, which means I have 5. Chlorines, I have 2. Calciums, I have 1. And oxygens, I have 1. Okay, I do always recommend, like I said, do your hydrogens and oxygens last. So let's look at our other elements. Nitrogen's 1, that's good. Cl's messed up. So let's do a 2 on this side for Cl, so that will change my nitrogens to 2. That'll change my hydrogens to 8 plus 2, which will be 10. And it'll change my chlorines to 2. Okay, now so let's make this other side. Let's fix my nitrogens, so, because that fixes my chlorines. So if I put a 2 there, that will fix my nitrogens. I will then need to recount my hydrogens. 2 times 3 is 6, plus 2 is 8. Okay. So I've got everything else. So I don't have hydrogen fixed yet. But I just need 2 over here. So let's do a 2 right there. If I do 2 like that, then that now makes my hydrogen 6 plus 4, which equals 10, which is how many I needed. And then when I recount my oxygens, I distribute that 2. 2 times 1 is 2. So I have 2 nitrogens, 10 hydrogens, 2 chlorines, 1 calcium, and 2 oxygens. Cha-ching. Done. All right. That one was a little more complicated. Like I said, these can be kind of complicated at times. So just be aware that it's really just counting elements. All right, so let me move my balance check. All right, I've got Zn. This one would be one where, again, I would probably recommend doing the water as HOH. So if I have Zn and Cl, let me go back to colors. So if I have Zn and Cl and H and O, and then I have Zn, Cl, H, and O. So Zn I have 1, Cl I have 1, H I have 1, and O I have 1. Ooh, I was about to write there. O. 1. Zn I have 1, Cl I have 2, H I have 1. If I look at it as HOH instead. And then for, oh, yeah, I don't want to look at it as HOH. Sorry. Yeah, that's not a good way to do that. Because I don't have OH on both sides. So yeah, that's not a good way to break that down. Which I didn't when I originally wrote it down. So I guess that's good. Hydrogens then, though, I have 2, and oxygens I have 1. So that's really easy to see that my chlorines and hydrogens don't match. So if I put a 2 here and just recount, that's 2 and that's 2, and everybody's good to go. All right. Sorry about that. I'm saying the HOH because, yeah, I didn't have OH on both sides. So hopefully that helps, and that goes through pretty much this is a huge chunk of your next test, and so I did a lot of examples. It's a long recording. I am sorry about that, but it is very beneficial, I feel like, of going over lots of examples. Okay? Y'all have a good one.